sigma notation. So first of all, we need to define what in fact a sequence is. A sequence is just an ordered list of terms, okay? It could be many terms, it could be a few terms. It's just an ordered list of terms. And so we're going to define what is known as a finite sequence. Finite, whenever you hear that number, or hear that number, hear that word, okay? Whenever you hear the word finite, it means it's a set number. It's either like 100 terms or 10 terms or 5 terms, but it is a set number of terms. On the other hand, when you hear the word infinite sequence, that means that the sequence goes on forever and ever and ever. And so how we signify it goes on forever and ever and ever is we use an ellipsis. And so what you'll do is you might see like the numbers here, 5, 10, something like this. And what that ellipsis means is that it is an infinite sequence. So we're going to talk a little bit about explicit formulas as well as recursive formulas today. An explicit formula gives a sub n as a function of n. And that's not going to make a whole lot of sense right now until we look at an example. So let's go ahead and look at this one. It says find the next 4 terms of the sequence. And you probably did this when you were littler, okay, especially like in elementary school. They would give you a list of things and you would have to fill in the blanks. Okay, so if I have the numbers 2, 7, 12, 17, what would be the next 4 numbers?
22.
22?
27, 32,
Yep.
37.
Okay, 32, 37.
How are you guys doing?
Now this is actually known as an arithmetic sequence. Okay, let's look at the next one. 2, 5, 10, 17.
Oh, 3,
26.
So, best way,
26.
what do you do to 2 to get 5?
3,
Add 3.
5,
You add 5 here. What do you add here?
9.
So the next one you're going to add 9. So that means 26. And then you're going to do what?
11.
11, which would mean 37.
12,
30,
Is that 50? And what would be the next one?
65.
65. Very good. So you're actually increasing as you go up. Okay? Let me go ahead and make that a little bit better. There we go. Let's look at the bottom one. What are you adding first? 1, 4, 5, 6. So what's this one going to be? 7, so it'd be 29. Then what? 30 what? 7. Then what? 46. And then what? 56. Okay. Now, this is what's known as an explicit formula. It gives a sub n as a function of n. And so what we need to do is we're going to find the first 4 terms here. So when we find the first term, that means you replace n with 1. When you find the second term, you will replace n with 2. So I'm going to start by putting in 1 for n. Okay. So very first thing you're going to do is the negative 1 to the first power. Okay. So what's going to be the number that you get? Okay, and then the final number will be? Negative 2. So now you're going to do the exact same thing, except for in place of 1, you're now going to put in 2. So you have negative 1 squared, which is 1 times 2 times 2, which is 4. Then you're going to do the same thing. You're going to replace this with 3. So what do you get? Negative 6. Just for kicks, what do you think the next one's going to be? Don't plug in the number 4 yet. Positive 8, so the next one would be negative 10, then positive 12. So you're seeing the relationship. We only need the first 4. Okay? All right, so the next one. We're going to start with 1, right? So you're going to do 1 cubed minus 10, which is what? Negative 9. Then you're going to do 2 cubed minus 10, which is negative 2. What's 3 cubed minus 10? 17. What's 4 cubed minus 10? 54. There you go. So that's just a matter of finding the terms in a sequence. Questions? Think you can handle that? Okay, so, oops, let's come back, sorry. we're going to talk about a recursive formula. Recursive formula is a little different. I don't know if you necessarily maybe need to write down what this actually is in terms of the words. I think you could probably write it down with an example. So what I would probably do in your notes is I would probably write out recursive formula, and then I would find the fifth term of the sequence. Okay, because this right here is a recursive formula. So a recursive formula is used to determine the next term of a sequence using one or more of the preceding terms. Now the root word of recursive is recursion. Recursion is something that keeps cycling. And so if I look at this, recursive formula will always have what the first term equals. So in this case, in order to find the fifth term, I need to find the previous four. So really what I need to do is I need to fill the blanks in here. 2, 3, 4, 5. And so that fifth one is what I want. It's not just a matter of you plug in the number 5 and you can get that. Okay. So let's go ahead and see what it says. It says that the first term is 1. So that's where I'm going to start. Now, what this says is this is always the preceding term. So if I want to find the second term here, this means the first term. So this means take the first term, add 2 times n minus 1. So in this case, the first term is 1. I'm going to add 2 times 1, 2 times 2, sorry, because I'm finding the second term, minus 1. So this would be 1 plus minus 1, which is 4. Now to find the third term, I'm going to take the second term plus 2 times 3 minus 1. So the second term is 4 plus 2 times 3 minus 1. So what's that going to be? 9. So then the next one, I'm going to take to find the fourth term, I'm going to take the third term. So what's the third term? 9, and I'm going to plus 2 times 4 minus 1. So what's that going to be? 16. Now to find the fifth term, I'm going to take what term? The fourth term, 16. I'm going to add 2 times 5 minus 1. And what do I get? 25. You already kind of see a pattern? What do you add here? 3, 5, 7, 9. So the next one would be 11. So find the fifth term of the sequence would be this.
Why does, how does the minus 1 versus a and minus 1, how is it just, oh, okay, never mind, I got it.
You got it? Okay. All right, so find the sixth term of each sequence. Same thing. So when we find the sixth term, we have to find the first 5. Okay, so the first one that we have here, a sub 1 equals 3. That means my first term is 3. So I've got 1, 2, 3, 4, 5, 6. First term here is 3. Now, what that says is if I want to find the second term, I'm going to take negative 2 times what?
3.
The first term. So I'm going to take negative 2 times 3, which is what? Negative 6. If I want to find the third term, I'm going to take negative 2 times the second term, which is negative 6, so I get 12.
What about the negative minus 1?
That's telling me that that's the third term. If I'm finding the fourth term here, and I plug in 4 here, that really becomes a sub 3. That becomes my previous term. That minus 1 says you go to the term directly to the left of that. So if I want to find the fourth term here, I'm going to take negative 2 times this term right here, which is what? Negative 24. If I want to find the fifth term, 48. And what's my final one going to be? Negative 96.
So, what is a 3 comma a and what's that?
There's 2 parts. The first part is that a1 equals 3.
Yeah, you might
Oh,
want to break that up for me.
I see what you're saying. Hey.
All right, so let's go ahead and look at the next one. So 6 terms again. 1, 2, 3, 4, 5, 6. What's my first term going to be? 8. Very good. Now, what this says is if I want to find the second term, I'm going to take 2 times the first minus 7.
11. Nice. Love.
Okay, 2 times the second minus 7. 11. 2 times the third minus 7. Okay. $23, you said? Okay, what's this next one going to be?
39.
39. So interestingly enough, I have 1, 2, 4, 8, and 16. Okay, so let's go ahead and talk real quick about this, kind of a little history lesson here. Okay? Leonardo Pisano from 1170 to 1250 was a medieval mathematician and businessman. He is most known as Fibonacci. Okay? Although he never gave himself that name. Fibonacci was taken from whatever that is. I think it's Filius Bonacci, which means son of Bonacci. So that's where his name came from, Fibonacci, is because he was the son of Bonacci. In 1202, he posed the following question in a book. How many pairs of rabbits will be produced in a year, beginning with a single pair, if in every month each pair bears a new pair, which becomes productive from the second month on? Okay? And this is actually where the Fibonacci sequence was created. Okay, and so if you look at this, it's 1, 1, 2, 3, 5, 8. What would the next number be?
8.
So look at the sequence. What do you think the next number would be?
12.
Nope. Not 12. Yeah. What's the next one?
21.
Good. What's the next one?
Next one. See how long lucky are. Ooh, lucky already. What's the next one, huh? Big small player?
Don't know it. What's the next one? Okay, now
Vegas is running.
let's look at this. How do you get 13?
8 plus 5.
8 plus 5, how do you get 21? 8 plus 13, how do you get 34? So you take the previous 2 terms and add them together. And so the Fibonacci sequence is seen in a lot of places. It's seen in pine cones. It's seen in nature a lot, with like the way the leaves are, okay, on a tree. Pine cones is one of the ones that you will see it more often. There's numerous uses. We will maybe talk about that a little later. We won't get to that. We've got to finish this lesson first. Okay, and so a series. Now, when I think about a series, no, not quite the World Series. Basically, it just means you take a sequence and you put pluses in between them instead of the commas. So a series means a sum. So a sequence would look like this. A series would look like this. And that's it. A series has pluses, a sequence has commas. And so we're going to talk about partial sums, which basically means instead of calculating the sum of the entire sequence, we're going to say, I want the sum of the first 3 terms, the sum of the first 4, the sum of the first 5. Okay, and so how you find the nth partial sum is that's denoted by S sub n, where n here indicates how many terms you're going to add up. It's found by calculating each term up to the nth term and then finding the sum of those own terms. I actually thought at one time this was really tough, and then when I actually figured it out, I was like, wow, that's pretty easy. Okay, so if I want to find S sub 3, you're going to add up the first 3 terms. If you want to find S sub 5, you're going to add up the first 5 terms. And so that's what we're going to look at now. And so if I look at this, it says find the 4th partial sum of. So what I want to do is find the first 4 terms, and then I'm just going to add them together. That's all you're going to do. So the first 4 terms, 1, 2, 3, 4. So my first term, I'm going to plug in 1 for n. If you plug in 1 for n for your first term, what do you get? 1. Plug in 2 for n. What do you get?
What?
7.
2 times negative, oh.
Negative 2
It's not 2
squared
times
plus 3. Okay, what is going to be the third term? Negative 5. What is the fourth term? 19. So remember, it's all about powers here. And so now, if I want to find the partial sum, all I'm going to do is add all those up together, and that's it. So what is 1 plus 7 plus negative 5 plus 19? 22. So that is the fourth partial sum. Now, real quick, what would be the third partial sum? 3. Okay? So that's all the partial sum is. Please don't. All right, so find the sixth partial sum. Find the sixth partial sum. So to find the sixth partial sum, and oops, I forgot to make this a subscript. This should actually be a little 1 here. So to find the sixth partial sum, I've got to find the first sixth term, or 6 terms, and add them together.
8.
What's the first term? 8. Good. The second one states I'm going to take the second, I'm going to take 0.5 times the first. Okay, so what's going to be the second term? 4. 0.5 times the second? 2. 1/2 or 0.5, yep. Okay, and then 1/4. So this would be like 0.5 or 0.25. Now all we're doing is we're just taking half of the preceding term, so now to find the partial sum, let's add them together. So 8 plus 4 plus 2 plus 1 is 15, plus 0.5 plus 0.25, 15 3/4, or 15.75. That is going to be your partial sum. So pretty straightforward, pretty easy. Okay? Questions? Okay, we've got a few more problems we need to end with, and that's what is known as sigma notation. And then these are going to go fairly quick. Okay, a lot of information today. Tomorrow we'll pare it down, and we're only going to cover something on arithmetic sequences and series. So sigma notation is basically a shortcut way to write a sum. Instead of writing out a bunch of terms, sigma notation allows you to do a shortcut way. We have what is known as the limits of summation. Now notice where those are written. Those are written above and below the sigma. Okay. You will see n equals 1 a lot. But basically, this one tells you where you start. So this says that we start at 1 and we go to 5. This right here tells me what am I going to sum. So I'm going to sum n plus 1. So how I would read this, and we call that the summand, by the way. This would be written or read as the sum of n plus 1 from n equals 1 to 5. So how I read that, I see the sigma sign, the sum of whatever's in parentheses from the limits of summation. Okay, so the sum of n plus 1 from n equals 1 to n equals 5.
So you're like doing the n plus 5.
You plug in, and, well, we'll look at that in the next example. I think that'd make a little more sense. So this one says find the sum. So this would be read as the sum of 4n minus 3 from n equals 1 to 5. So I'm going to start with n equals 1. Oh, I have the pen. Silly. Okay, so here's n equals 1. And then I got n equals 2. And then I have n equals 3. And then I have n equals 4. And then I have n equals 5. So what I'm going to do is I'm going to plug in 1 for n. And when I do that, what do I get? 1, because you have 4 times 1 minus 3. I'm going to plug in 2 for n, 5. 3 for n, 4 for n, and 5. So now it says find the sum. So what am I going to do with all those numbers? Add them together, and there you go. Okay. 45. Now, those of you wondering how you can get it so quick, let's make 30 here, make 10 here, so there's 45. All right, next one. Find the sum. So this is the sum of 6n minus 3 divided by 2 from n equals 3 to 7. So I'm going to start. n equals 3, n equals 4. Now, you will always use your whole numbers. Okay, you will never use fractions, so you always use your whole numbers for n. So if n is 3, what do you get?
7.5.
7.5, so 15 over 2. 4, what do you get? 21 over 2, very good. 5, what do you get? What? So now let's go ahead and try and make something's over 2, so this makes what? 60, right? What do these two make? 60, so you have 60 and 60, which is 120. So 135 over 2. So that's the sum. Questions? Think you can handle that?
Quick question.
Yeah.
Does it always need to be like over 2 or something like that?
No.
When it's in the decimal point?
I would prefer fractions unless it's impossible to do.
That's just what I like.
So let's look at this one. Now this one's different.
Infinity.
It has infinity.
Just leave that like that.
Now infinity, remember, means it keeps on going forever and ever. But this is actually one that, believe it or not, how it is written, it will actually approach a specific number. It won't ever meet the number, but it's going to get close and close. And it actually illustrates, okay, convergence, and it illustrates something known as the concept of a limit. So what we're going to do is we're going to just do 1, we're going to do 2, we're going to do 3, and we're going to do 4, and we're going to add it up, and we're going to say, okay, in our mind, what do we think this is going to add up to be? So I plug in maybe a little bit if we have time. I don't think we'll have time, though. You'll hit it next year a lot, though. Okay, so if n equals 1, what is 6 divided by 10? 0.6. Okay. Now you all have your calculator. So what is 6 divided by 100? Because that'll be the next one. 0.06. The next one will be, what'd you say? So do you see the pattern? What? Everything is always, it's going to be 0.0006. So really, if I add these together, I'm going to get 0.6666, correct? And the ones I keep adding on are always just going to keep adding a 6. So what is that going to approach? 2/3. Because if I keep adding a 6, it's going to eventually keep going nonstop, and it's going to be 2/3. All right, so let's go ahead and look at your book real quick. Let's look in your book real quick, because this is what I have down. Let's make sure that this is good. So page 595.
Holy cow, Mrs. Boozer. I don't have all the time in the world.
So page 595, 1 through 10. That's just like the ones we did in class. We have 28 and 29, which is find the partial sum. And then we have 36 through 45, which is find the sum. Okay? I will actually cut that back, 36 through 44, the evens.
Yes.
Okay, so 36 through, that's the only one that you'll have evens on. Okay, so that is actually due tomorrow. Okay?